Thank you for introduction. I'm Tamami Okamoto, a postdoc researcher in Tsundaori Institute, Shanghai Jiaotou University. Today, I'd like to introduce the current understanding of carbon abundance in protoplanetary disks. At first, the planet formation starts at the protoplanetary disk around the central star. At first, most of solids in disk exist as dust aggregates. The size is less than 1 millimeter, and it starts grow up to the pebble size, and then to go to the planetesimal size about 10 kilometer. Also, it starts to grow up to the protoplanets. Finally, it becomes to the planet size. Then, in this talk, I mainly focus on these dust aggregates and pebbles in a protoplanetary disk. In the classical planet formation models, the planets formed very locally. For example, this figure shows that the schematic view of the planet formation theory. At first, the pebbles and dust grow up to the planetesimals, and where planetesimal forms is that the place of the local density of pebbles and dust are very high. Also, the planetary core can accrete only the nearby planetesimals and then grow up to the planet size. So then the chemical abundance of planet should be corresponding to that of the pebbles and dust where the planets formed. In this talk, I focus on the carbon abundance because it's important to determine the planetary atmosphere. Because I'm not the expert of this part, so then I introduce very briefly. If the carbon cycle exists in the rocky exoplanets, the atmosphere is more CO2 rich. But if there are no carbon cycles, the atmosphere should be methane rich. So then to understanding the carbon cycle, it's important to understand and predict the exoplanet atmosphere. Also, the carbon abundance observed by James Webb telescopes recently, for example, exoplanetary atmospheric CO2 ratio and the gas phase CO2 ratio of the protoplanetary disks. So then the carbon is important to understand not only the planetesimal formation theory, but also the observation of the exoplanets and disks. There are many previous studies on the carbon abundance in the protoplanetary disk, but the problem is that the carbon abundance is not theoretically revealed. This is my take-home message that the number of previous studies to reveal and investigate the carbon abundance of the protoplanetary disk increasing, but there are several remaining problems. The main problems are the carbon deficit problems of the inner solar system bodies for solid phase, and the uncertainty of the gas phase CO2 ratio of the disks. At first, I start to talk about the carbon deficit problem. This figure shows that the carbon mass fraction of the solar system bodies. The carbon abundance of the comets is similar to the interstellar medium dust and the sun, but for the Earth, the abundance is about more than 2 orders of magnitude lower than the comets, and the chondrites is also depleted in carbon more than 1 order of the magnitude. So then the inner solar system bodies are depleted in carbon. The carbons in the comets exist as refractory components. For example, organics, amorphous carbon, graphite, and PAH. This table shows that the temperatures to vaporize these refractory carbonaceous solids. For graphite or PAH, it requires more 1000 Kelvin to vaporize. Also, the organics requires to more than 300 Kelvin to destroy these organics. These temperatures are higher than the disk temperature around the Earth orbit. To considering the existence of these refractory carbons, the carbons should be destroyed inside the Earth orbit. So then this figure shows the schematic view of the carbon mass fraction. The fraction should decreasing at inside the Earth orbit, and the fraction of Earth should it's expected to similar to the comet abundance. But the observation shows that the carbon abundance of the Earth is more than 2 orders of magnitude is depleted in the comets. So then it is mystery why bulk Earth is depleted in carbon compared to the comets and the Sun. One possible mechanism to replicate the carbon deficit of the Earth is thermal decomposition of organics. In this talk, I call this reaction as pyrolysis. So then the destruction temperature for organics is relatively low. It's about 300 to 500 Kelvin. So then if the destruction temperature comes outside the Earth's orbit, the carbon fraction should be lower than the comet's value. To explain the carbon deficit, there are some deficit by the thermal decomposition. There are some requirements. First, the destruction temperature should be outside the Earth's orbit. So, in other words, the disk temperature around the Earth's orbit should be higher than the 500 Kelvin. This high temperature can be replicated by the viscous heating of the disk for the first stage, or FE Orionis, like outburst of the Sun. The requirement is that the low mass fraction of remnants. Remnants it's like the suit of thermal decomposition. If you put the cake in microwave and waiting for a very long time, the inside the microwave some soot-like materials should exist. This is a remnant of thermal decomposition. So then, to replicate the low mass fraction of the carbon, the remnant should be lower than the 1% of the organic mass. But this mass fraction is uncertain by experiments. As a requirement is that the high mass fraction of organics in the all refractory carbons, because as graphite or PAH, amorphous carbons cannot destroy it around the 500 Kelvin. So then about more than 90% of refractory carbons should be organics to explain the Earth's carbon fraction. But in the interstellar medium dust, there are non-negligible abundance of the amorphous carbon or graphites. Also, the comet Halley has abundance of graphite or amorphous carbons. So then these requirements could be inconsistent with the observations of ISM dust or comets. Another possible mechanism to replicate the carbon deficit is the photolysis or oxidation. These reactions can occur in the upper layer of the protoplanetary disk. For oxidation, in the upper layer, oxygen atoms exist, and when it collides to the carbon dust, it's oxidized and the CO gas are released. So then finally, the dust becomes carbon poor. Also, FeV photon from the central star cut the carbon-carbon chain in the amorphous hydrocarbons. So then when the carbon dust exposed by the FeV radiation, it can be also carbon poor. This mechanism can also vaporize the not only organics but graphites and amorphous carbons. But this mechanism also has several requirements. At first, this mechanism needs the additional mechanisms to stop the flux from the new refractory carbons coming from the outside this region. This figure shows that the time evolution of carbon fraction when we didn't consider the radial motion of the solids. So then black line is the final result. Then the carbon abundance of the Earth is depleted compared to the cometary value. But considering the radial motion of the solids, new refractory carbons coming from the outer disk region, and it cancels out of the depletion of the carbon by photolysis or oxidation. So then if you stop the flux of refractory carbons by the Jupiter, because Jupiter makes a gas gap and the solid particles can stop outside the gas gap, then the carbon abundance around the Earth's orbit can be decreased.
Sorry, can I ask
yes. Okay.
Yeah, sorry, can you clarify the Gauss mechanism for the carbon walls? Is it the refractory carbon is evaporated and being photolyzed and oxidized into CO, maybe CO and CO?
Yes.
And then this becomes an irreversible loss for refractory carbon, or is it something else?
Yes. So then when the refractory carbons destroyed, the carbon atoms can be converted to the volatile gas species. So as you said, the CO gas or CH4 gas. These volatile species cannot condense on the Earth's surface. So then to considering only the solid phase of the Earth, the carbon mass fraction becomes decreasing. It's okay. So, sorry. What is your question? Okay. Thank you. Okay. Then another possible mechanism to stop the refractory carbon flux is that the fast decaying of the flux coming from the outer disk region. When the acid pebbles are formed in the outside the H2O snow line, the acid pebbles first drift inside the snow line within the 0.5 million years. In the later disk stage, the flux coming from the outside the snow line is negligible. So then the flux of new refractory carbons seems stop. So then the carbon fraction starts decreasing. This model also requires high vertical turbulence. This figure shows that the time evolution of carbon fraction for different turbulence strengths. So then the horizontal axis shows that the time and the vertical axis shows that the carbon fraction. This green line shows that the high turbulence case, and the red one shows that the low turbulence case. So then if the vertical turbulence is low, the carbon abundance cannot decrease for about the several 100 years, because the oxidation and the photolysis only occurs in the upper layer. So then the more dust are lifted to the upper layer by the turbulence. So then the to occur efficient oxidation and the photolysis requires that the high efficient particle mixing of the dust particles and high turbulence of the disk. But this high vertical turbulence suppresses the planetesimal formation. This figure shows that the case of the vertical high turbulence and the low vertical turbulence case. In the planetesimal formation theory, we consider that the most of dust and pebbles are settling down on the midplane. So then the solid's local density is high enough to occur planetesimal formation. But for efficient oxidation and photolysis, we need the high vertical turbulence. So then these two requirements can be conflict with each other. From the previous slides, I talked on the carbon abundance of the solar system, but nowadays the carbon abundance of exo-rocky planets can be observed. This figure shows that the carbon CO ratio observed in the white dwarf photosphere. If the exoplanetesimals or exoplanets accreted in the on the white dwarfs, the chemical abundance of these bodies appears as pollution of the photosphere. So then this plot shows that the C/O ratio of the white dwarf pollution, and the lowest value is lower than the Earth's value, but the higher value is the value is between that of comets and chondrites. So then, to focus on the exoplanets and exoplanetesimals, carbon abundance has a wider range. Then, and this figure shows that the C/O ratio of the solid phase for the different turbulent strengths and different solid size. So if the vertical turbulence is low, the carbon abundance should be higher than the high turbulent case. So then this very wide range of the carbon abundance of exoplanets might imply that the different properties of the disk, for example, the turbulence or particle size. This is a summary of the first half. The main remaining problem is that the carbon depletion of the inner solar system. There are some probable solutions to replicate the problems. One is the thermal decomposition of organics, and the other one is the photolysis or oxidation in the upper layer. But this solution has the requirements. For example, the thermal decomposition requires the very low mass fraction of remnants and the high mass fraction of organics. But these requirements might be inconsistent with the observation of ISM dust or comets. The other possible mechanism, photolysis or oxidation, requires the additional effect to stop the refractory carbon flux coming from the outer disk region and the high vertical turbulence. But this condition may be conflict with planetary formation theory. For the first part, is there any questions? Okay, so go ahead. So then, I talk about the gas phase C/O ratio of the protoplanetary disk. Nowadays, the JWST observed the many atmospheric abundance of the gas giant exoplanets. This figure shows that the C/O ratio of the atmosphere estimated by XCOMPS. So the vertical axis shows that the C/O ratio of the atmosphere. So then the solar value is about 0.6, and there are many wide abundance of the C/O ratio. This value is important to expect the migration history and the planet formation history of the exoplanets. In classical model, they use this figure coming from the Uberg et al. 2011. This figure shows that the C/O ratio in solid phase and gas phase, considering the only H2O, Cu, and the CO2. CO2 in protoplanetary disk, and they plot this figure only consider the evaporation of these three species at the each evaporation line. It's a simple time model, but there are some remaining problems. Uberg et al. 2011, they considered this ice in the protoplanetary disk. So then that the all CO released inside the CO snow line, and the CO2 ice only released that the inside the CO2 snow line. But there are other possible positions to release the carbonaceous gas. For example, the CO and the CO2 ice also trapped in the amorphous ice. For example, so then if the CO and CO2 is trapped in the amorphous H2O ice, it's released by the crystallization of the ice. This is a schematic view of the crystallization. So then at first the CO and CO2 gas are trapped in the pore of the H2O ice. But when the H2O ice crystallized, the volume of the pore was decreasing. So then the trapped CO and CO2 ice are released from the pore. This temperature is about 130 Kelvin, and between the CO2 and the H2O snow line. So then this additional position to release the carbonaceous gas can be changed the CO ratio of the disk. Also, as I talked in the first house, the carbonaceous gas can be released from the refractory carbons, such as organics and amorphous carbons. So then, to considering the photolysis and thermal decomposition of organics, pyrolysis, the carbonaceous gas can be released in the inner disk region. After that, I focused of the carbonaceous gas released from these reactions. This figure shows that the CO ratio of the protoplanetary disk considering the only pyrolysis or photolysis. In the upper layer, this figure shows that the result only considering the pyrolysis. The carbonaceous gas are released this about the 300 Kelvin, like about 0.3 AU. For the low turbulent case, the CO ratio increases inside the snow line. On the other hand, if we only focusing considering the photolysis, the CO ratio increasing in the outer disk region, around the outside about 30 AU. So then, to considering the different chemical evolution of the refractory carbons, the high CO ratio region becomes different. But we don't know which mechanism contributes more to CO ratio when we consider both of these effects. So this is the result of the considering both of photolysis and pyrolysis for the different turbulent strengths. Then the most of then the organics are somewhat decomposed this alpha line from here and here. For the low turbulent case, that the CO ratio increasing around the pyrolysis line. But for high turbulent case, the CO ratio doesn't increasing inside the H2O snow line, but mainly increasing outside the H2O snow line, especially between CO2 and CH4 snow line. Also, we changed the particle size. This figure shows that the larger case, and this figure shows that the smaller particle size case. Similarly to the low turbulent case, the CO ratio increasing around the pyrolysis line when the solids are large. Also, that the smaller solid particles case is similar to the result of the higher turbulent case. So then the CO ratio doesn't increase around the pyrolysis line, but increases between CO2 and CH4 snow lines. This is the schematic view of the what's happened for the large particle case. If the solid particles large enough to decouple from the disk gas, the radial drift speed is very faster than the gas velocity. So then the organic solid particles drift very fast. And then this line shows the pyrolysis line. And organics can be, most of organics can be converted to the gas phase. So then the carbonaceous gas enriched inside the pyrolysis line. But when the drifts of the organics large particles finished, very less abundance of the organics can come from the outer disk region. And also these enriched carbonaceous gas diffuse out to the outside the pyrolysis line. So then finally the carbonaceous gas abundance inside the pyrolysis line starts decreasing. This figure shows that the CO ratio of the gas phase for the at the 0.3 AU for different time. At 0.1 million year, the CO ratio increases where the dust particles are large enough to decouple from the gas, showing from the upper region of this dashed line. But after finishing the flux of organics coming from the outer region, the CO ratio starts decreasing. So this dotted line shows that the time scale where the carbon enriched carbonaceous gas inside the pyrolysis line decreasing. So then the upper region of this dotted line, the CO ratio comes decrease. Also, finally, 3 million year, no results shows that the silver ratio, high silver ratio, because that the most of region upper the this dotted dashed line is coming from the longer time scale than the decaying of the enriched carbonaceous gas. Also consider for the photolysis. As I mentioned in the first half, the photolysis requires efficient vertical mixing. So then the this figure shows that the ratio of the gas phase at 30 AU for the different turbulence and the particle size. The silver ratio increasing for the higher turbulent case. Also, for the efficient oxidation photolysis, it should be many solid particles in the upper layer. So then, if the particle size is large, the most of particles is settled down at the midplane. Then the efficient photolysis also requires the small solids, and this is corresponding to about the Stokes over alpha is less than 1. So then this line shows that the time scale of the photolysis decaying photolysis destroys carbonaceous solids by roughly estimated the vertical mixing time scale and the abundance of the solids in the upper layer. So then the silver ratio can increase in the lowest region of this dotted line. Nowadays, the silver ratio of the protoplanetary disk also observed, and especially for the very low mass stars, the disk around the stars shows that the high gas phase silver ratio inside the H2O snow line. This figure shows that the observed results, and the horizontal axis shows that the age of the disk, and the vertical axis shows that the silver ratio. So then this figure suggests that the silver ratio increase with the time. This several previous studies focused on this trend, and this can be replicated by the depletion of the H2O water vapor, or conversion of CO gas to the other species, CH4 or C2H2, by the chemical reaction. Also, we found that the photolysis can increase the carbonaceous gas abundance with the time, but these effects could overlap to replicate this trends to increase the silver ratio with the time. This is a summary of the second half, considering the gas phase silver ratio. The problem is that there are many possible positions to release the carbonaceous gas in protoplanetary disk, and the number makes it difficult to understand the gas phase silver ratio finally. In this talk, we only focus on the contributions of pyrolysis and photolysis on the silver ratio. We found that if pyrolysis can be dominant when solids are decoupled from the gas, and the pyrolysis increases the silver ratio inside the H2O snow line. On the other hand, photolysis is dominant when the vertical disk turbulence is strong, and the carbonaceous gas released by photolysis increase silver ratio between CO2 and HCH4 snow line. Our result can be applied to the observed high silver ratio inside the H2 snow line. So then, this is a summary of this talk. Take-home message is that there are several remaining problems to understand the carbon abundance of the protoplanetary disk. The main problems are the carbon deficit of the inner solar system bodies. For the gas phase, that's the uncertainty in the silver ratio of the disk gas. It's also important. Sorry. Yeah. Okay. It's also important that these problems are more complicated by the sensitivity of the carbon abundance to the disk turbulence and the solid size. That's all my talk. Thank you for your attention.